All right, there's one last pre-calculus topic that I wanted to take a look at before we dive into the meat of the course, so to speak, and that's the notion of a logarithm. So again, this shouldn't be brand new territory for anyone, but just in case, a bit of a reminder. So logarithms are just another way of writing exponents, essentially. So I've got an equation written here: y equals the log base a. That little subscripted a is what we call the base of the logarithm of x. So I like to put the parentheses. Textbooks don't always do it, but that's just, that's the way I do things. So saying that y is equal to the base a logarithm of x is in fact one and the same thing as saying that if we were to take that base a and then raise it to the y power, y, anyway, we'd get x back. So, for instance, 2 is the base 10 log of 100 because we take our base 10 and our y squared is in fact 100. So yeah, again, it really is just sort of a rewriting of the exponential, structure that hopefully we're kind of already comfortable with. So I did want to mention, just along with this, there's a handout sitting in our Moodle course that covers a lot of like the basic properties. So it's like a one-page recap of like important things you would need to remember about how logarithms work. So I did want to take a look real quickly at a couple of special cases of logarithms that we deal with, because technically there's like an infinite number of them. Any positive not equal to one number has its own logarithm. You have base 2 logs, base 5 logs, what have you. So we already saw one of the two I wanted to talk about, the base 10 logarithm. It comes up frequently enough that we kind of dispense with writing the subscripted base here. We just call that log of x, or the common log. You'll often hear it referred to. And if you look at your graphing calculator, it has a button on there labeled LOG. It is specifically for calculating base 10 logarithms of numbers. So it sees use in a fair number of applications. Things like the Richter scale we use to measure the intensity of earthquakes, the pH scale we use to measure the intensity of acids and bases in chemistry, decibels, the sound intensity, measurement. Yeah, those are all working on sort of a base 10 logarithmic scale. So surprisingly enough, that's not the one we're going to be using most often in calculus. We're going to be using a different logarithm. And no, that's not a mistake. You may remember this again, that this is a base E logarithm. So E is an irrational number. It's approximately 2.71828. There's another 1828 after that, but then it quits repeating. But so we use that logarithm actually more often than we would any other log in a calculus context. We refer to that using the letters ln for natural logarithm. Again, I want to go ahead and say this in advance. I know it feels like possibly the least natural thing on the planet that we pick this number as a base for, a logarithm. When we get to the right calculus concepts, you'll see exactly why we like this particular logarithm. So, I promise, there's an answer there. I just can't really, show you the cards in my hand yet. I promise, we'll get there. So there are some other log properties that show up on the handout. I just wanted to look at a quick example of one of, as I said, so sort of the properties in action, and then I want to see how we can use logs and exponentials to solve some equations. All right, so as an example of this in action, so if we have, I'll just go, I'm going to go with the natural log, because like I said, I'm a math teacher. The base E logs are really the ones I like. So I've got 2 times the natural log of x plus 1 minus the natural log of 3x plus 2. So we're going to use our properties of logarithms as on that reference sheet. sort of to collapse this thing down into a single logarithmic expression. I'll refer to that as collapsing or condensing, the logarithms. I try not to use the word simplify because it feels like that's an eye of the beholder thing. Anyway, so our properties of logarithms, they tell us two things that'll help us out here. One, we have a coefficient sitting out front of a logarithm like this. So the property is written on the handout says that you can drag exponents out front of a logarithm into a coefficient. We're going to use that property in reverse. We're going to take this guy and kind of slurp him back up into the logarithm. So we have 2 times, not 2. I said I just got rid of him. He's supposed to leave. He didn't listen. Did you see that guy? He's a punk. Anyway. So the 2 hops up as an exponent inside the logarithm. I'm using the extra brackets just to make sure we're clear as to what's going on. So we still have the minus 3x plus 2 hanging around at the end. Okay, so now we've gotten rid of the 2 out front. Now we have a logarithm of one thing minus a logarithm of another thing. Looking at the log properties on the reference sheet, a subtraction like this, it turns into a division of the 2, arguments of the logarithm, so to speak. So we have natural log of x plus 1 quantity squared, and down below, so kind of like we saw with our exponent properties, that, a minus here, it's like, corresponds to a division thing. So yeah. All right, so the ln of x plus 1 quantity squared, if you wanted to FOIL that out, you could. It's not necessary for this, but for what I'm trying to show here. Over 3x plus 2. And we chop this down. More often than not, you probably actually want to go in the opposite direction with this. You would take an expression like this and then sort of use those log properties to take it apart into smaller bite-sized pieces. That's kind of why we came up with logarithms in the first place, to collapse down big numbers into things that were a little more manageable and to take complicated operations and streamline them. But I digress. I said I was going to talk about how we can use logs and exponentials to solve equations. Let's do that. Okay, so I've got an equation. Right now, we want to solve this thing, I should say, for x. So x is the thing we're after. We want to get it by itself. The problem is it's stuck inside this logarithm. No, we can't just divide both sides by ln. This is not like a multiplication like we saw with the function notation earlier. But as it turns out, we can use an exponential to get rid of these things. It turns out the exponential and the logarithm for the same base are what we call inverse operations. So yeah, applying one then the other, basically kind of they see each other, out of the dance hall. So if we sort of exponentiate, I think is the appropriate verb to use to describe this. It's really awkward to try to say it, and if I remember right, like Microsoft Word doesn't actually think exponentiate is a word. So anyway, but same old algebra principle. I raise e to the power of this thing. Whatever I do to one side, I got to do to the other. Thus, I have that thing equals e squared. As I said, it's not really appropriate just to slash through these like they're canceling, because then this is just like hovering in an exponent. But if you use that as a mnemonic, I get it. Anyway, so in any case, the natural log and the exponential, they go poof, they vanish in a puff of logic. On the right-hand side, we have e squared. You could work out a decimal for it if you'd like. I'm perfectly fine with e squared as a number because math teacher. Anyway. So then, like Algebra 1 style, to get x by itself, we've got to add 3 to both sides of our equation. So we get e squared plus 3. If you wanted a decimal for this, I came up with 10.389, accurate to 3 decimal places. So, yeah. So we were able to use an exponential to get a variable out of a logarithm. So what happens if we need to go the other way? That's an excellent question. All right, now we've got our variable trapped up in an exponent. 200e to the negative 4x equals 15. We want to get x by itself. Now, you might kind of sort of jump at this and say, aha, I see an exponential, I'm going to need to take a logarithm. Technically, you could, but I think it's easier if you go ahead and before you do that, get this exponential piece by itself. Otherwise, you've got to start busting out log properties to play around with stuff. You can do it. I think it's just easier if you go ahead and get in the habit of getting this guy by his lonesome. Anyway, so first off, we have e to the negative 4x. To get rid of this, since it's multiplied on, I have to divide. So 15 over 200. And like I said, you can simplify this down. I guess it would be, what, 3 over 40, I think. So, yeah, both of those should be divisible by 5. All right, so nom, I'm apparently hungry. Yeah, that was supposed to say now. All right, so now I'm leaving some space because I'm gonna, fill it back in here. So we take a natural logarithm. It's the same logarithm that matches our exponential base. So we have ln of 3 over 40 on the other side. Again, these are inverse operations. So the natural log and the exponential, they remove each other from the calculation, and all we're left with is this. Alternatively, you could pull the negative 4x out front, and then the natural log of e is just 1, because e to the first power is e. Anyway, so negative 4x, now we can sort of ignore the middleman here, and we have negative 4x equals this guy. So natural log of 3/40 divided by negative 4. If you'd written it out front as a negative 1/4, I'm fine with that. Let's see, and I got positive 0.648 as a decimal representation of that thing. So, all right. So, exponentials, logarithms, what they can do for us. We'll see these guys some more as the semester rolls on, but that actually brings what I'm wanting to do as far as pre-calculus to a close. So, congratulations, achievement unlocked. So, later on in the week, we'll actually do some calculus.